So we saw the time independent Schrodinger's equation, and the only assumption we started out with was that the total energy, potential energy, kinetic energy are all constant. None of them is dependent on time. So in such cases, that equation which we just derived holds perfectly true. But you do not always have a situation where all quantities are constant, right? There are times when your total energy, of course, will always be constant because of the law of conservation of energy. But your potential energy and kinetic energy can keep fluctuating. One might increase and the other decreases with time. That variation can be there. So when that dependence of time is there, your time independent equation will not work, which is why we have another equation called the time dependent equation. So here again we start with the original equation which we derived over here, a e raised to minus I by h cross et minus px. So for the time independent case, we split it into two equations, one in terms of position, one in terms of time, and we ignored the time part of it because we went with the assumption that nothing depends on time. But here, because there is a dependence on position as well as a dependence on time, we cannot do any splitting. So we take the entire function as it is, and we go about with the same procedure. You differentiate once, you get minus IE by h cross times the same function itself. So again, I and h cross are constants, so you take them to the opposite side. I h cross dou by dou t. Here we are differentiating with respect to time, notice that. So I h cross dou by dou t of this function gives me E times this function. So again, there's an operator, there's an eigenfunction and an eigenvalue. So in the time dependent case, the operator is I h cross times the first derivative with respect to t. The eigenfunction again is psi of x comma t, the entire function as such, and the eigenvalue is E, total energy. So this, so yeah, we had that equation. We'll keep that in mind now, but before we proceed with that, we come back to something we already know. Energy is kinetic plus potential, which is p squared by 2m plus v, which we already saw over here. But here in the time independent case, p and v were constants, whereas in our time dependent case, both of them are a function of x as well as t. So that is why we have this expression, energy is p squared of x comma t by 2m plus v of x comma t. What does it imply? It means that p and v are both functions of x and t, meaning they both vary with position and time. So we take this equation and we multiply with psi of x on each side first. So E psi x comma t is p squared by 2m psi x comma t plus v of x comma t psi of x comma t. We have simply multiplied it with the wave function. Now what we do is we replace with the corresponding operators on each side. So we have an E here and we have a p squared over here, and we just derived this operator for E. So E psi x comma t is the same as this operator times psi of x comma t, right? So where I have E psi x comma t, I will put that expression. And for p squared again we had where is it? This is for p. So because this is the expression for p, when you square it, you will get the expression for p squared. So just to give a quick recap of what happened, we had this equation for energy in terms of p and v. We multiplied both the left and right hand sides with the wave function psi of x comma t, and then wherever we had this expression which could be replaced by an operator, we did the replacement. So for E psi x comma t and for p squared by 2m, for p squared we did the corresponding substitutions, and this is the expression we get. So that's what is happening here. We took energy equals potential plus kinetic, we multiplied it with psi of x comma t, and we replaced all the, wherever we had the psi of x comma t, and wherever it was possible to replace it with an eigen operator, we did the substitution, and we arrived at this equation which is present in the pink box. So this is the time dependent Schrodinger's equation. So this is again very similar to your time independent. You have a h cross squared by 2m term, you have a term of potential, and you have your wave function. The only extra fitting here is that you have something in terms of t also, which makes sense because that was time independent, this is time dependent. And again, why do we do all this? Same point. If I know the energy, I can find out the position or vice versa. So given one quantity and given the value of psi of x comma t, using this equation I will be able to find out the other quantity which describes my wave. So that is the point of this whole manipulation.